Okay, so I'll take a little talking walk up to 478. So as I work through these other pages, 476, we're looking to do things with if chords are congruent, then arcs are congruent. If arcs are congruent, chords are congruent. There was a thing with tangent secant theorems, which is a setup like this. That this angle compared to its arc is also, anybody remember that relationship? An angle like this compared to that arc is half. So that's in this. And then 478, we're doing a bunch of stuff with that. The other thing going on with this, and I don't think I told you this the day the assignment came, as I look at 478, to do number 11, the instructions to do number 11 are found in number 10. We didn't do number 10. They proved a number 10 in their minds, but we didn't do the proof of 10. But the paragraph in 10 is how you do 11. Then there's a paragraph in 12 that we skipped the proof. But the paragraph for 12 is the recipe for how you do 13. So if you were doing this homework and you're like, how do I do 11? Read 10. Or if you were asking, how do I do 13? Read 12. Like those are the instruction manuals of how to do 11 and 13 are in the problems beforehand. If you did those without reading those instruction manuals, what you probably did was cheat by looking at the back, because those were odds. So don't do that. 478, anybody have stuff on 478 that had you hung up? Other than those two looked like obvious hang-ups for me, because I don't think I had told you to do that. 478, anything? And I'll take a little bit of a talking walk up farther. When we get out of that page and we take the leaf through the pages, there's the two tangent theorem, which is going to look like a picture of an ice cream cone. So if you try to do the 484 homework, a pretty good start for most of the questions early is draw yourself an ice cream cone. The two tangent theorem is telling you that these two segments compared to each other are congruent. You'll use that pretty much every time. The other thing you occasionally might use is if you find the center and draw a line, those angles are congruent. You're barely going to use that. But that's like a tiny bit in this homework. But the two tangent theorem is in there, and then these power theorems are in there. So let me do the power theorem stuff from the quiz we just did. So here's a point. If I want to find the power of that point, what is the power of that point? 40. The definition we do on the vocab is that you multiply the two lengths from the point to the circle. So we have a 4. We have a 10. The power of that point is 40. That has to be the result of any path we follow. So if you try to do this partially complete path, who's 5's friend to make the same 40? That is an 8.
Oh yeah, I think I put that.
Question about that, game? Okay, so if I go pick this point and I follow this path, it's not 4 times 5.
It's 9.
4 times 9. Because the full path we have to figure out is 9. 4 for the short way to the circle, 9 for the long way to the circle. 4 times 9 is 36. So all roads have to lead to 36. 36 is the power of that point. So what is this? 6. You only had one path that time, so it's got to be something times itself. 6 times itself to get you 36. For this, if I investigate this point, it's not 4 times 4, it's 4 times 8. So 4 times 8 makes 32. All roads have to lead to 32. This road is 2 times a big number, 16. I don't want the 16, I wanted that piece of the 16.
What?
14. The 16 minus 2 to get the 14.
Oh.
That's what you're doing on 484. So I don't know if that page is maybe the most familiar page because we've done that on the quiz the last 2 days. Did anybody have anything 484 that has you hung up? Then I'll continue to just take a walk So when we get up to the last section of reading, it was circles. So it was equations of circles, and trying to do stuff with equations of circles.
But there's no proofs.
There were no proofs,
Cool.
which is always a happy news. There were no graphs either. I graphed you a few, and now that I'm looking at this, I don't think they made you graph anything.
Yes.
I don't see it on a quick skim. Anybody do that and encounter anything that said graph? I'm not seeing it on my skim. I thought it did, but I don't see it right now. Did anybody need stuff 492? 492 stuff that was that?
6.
6. Okay, 6. So let's start off with the equation. If we go to write an equation of a circle, what's it basically look like? It looks like the distance formula. So I'm going to need to put some x's, parentheses, squares, y's, parentheses, squares, minuses, equals, plus. And then how do we get these filled in? From what item though?
The X and the Y, or the A and the B.
Yeah, where would it be on the picture of the circle though? These numbers would tell us the
Center.
center. So the center is what we're gonna rely on to get those blanks filled in. How do we get this thing filled in?
Radius.
That involves the radius. So if we go to do 6, they say the center is 2, 3. So this is a 2, and this is a 3. To figure out the radius, we're going to have to do something with that 6, 6. So I have 2 ways you could do that. So one thing, anybody have an idea? We need to figure out, like, draw a sketch. So we're 2, 3, that is the center. Six, 6 is a point that's on the circle. So we've got a thing like this. 6, 6 is on the circle. 2, 3 is the center. How can you figure out how far that is? Because that's going to feed, that's the radius that's going to feed into this. Well, people were thinking, you okay with what I did so far? That was your question.
Yeah.
Anybody have a thought on how you could
use the distance formula?
We could use the distance formula. Okay, so that would be a perfectly valid choice, would be flashback, use the distance formula, look it up, use it. Distance formula would give you the radius. That's true. Anybody have another way we could go?
Triangle.
How far over did I just go? 4. What did I go up? 3.
3, 4, 5.
3, 4, 5. So that would be another way you could do that.
That's easier.
There's a third way we could come up with this number, is plug 6 in here. 6 minus 2 is 4, squared is, remember that number. Put 6 in there, 6 minus 3, 3 squared, 9. What number are you remembering? 16 plus 9, 25. Which is also the 5 radius, however we got it. If you got it squared, could get you 25. There's a bunch of ways you could come up with that number.
Interesting.
Either a distance formula or make a triangle. Pythagorean, if you remember, the distance formula was the Pythagorean theorem. Like square add root, that's what the distance formula was. Or just plugging, like algebra flashback, plug the numbers in.
I'm just doing the equation, right?
Yeah, you're just doing the equation. Yep. So if it's me, personally, I don't think I ever draw that picture. I know the x minus 2 squared and the y minus 3 squared, and then if they want me to use 6, 6, I think I just plug the numbers in and just, it's going to equal wherever the math leads me. you have something else on that page? Nope. I would do the same thing on 3. For 3, what I would do to do 3, I would plug the numbers into the equation. And if I hit exactly 36, am I interior, exterior, or on the circle?
On the circle.
On the circle. What if I hit less than 36?
Interior.
And if I hit more than 36?
Exterior.
Okay, so what 3 boils down to is a lot of plug-in game. So does 2. 2, you just plug in the games, and if you plug in the numbers, if it equals 25, you'd say, yup. And if it doesn't equal 25, you'd say, nope. But the plugging into these equations can answer a handful of the 492.
Action.
So we're hitting up homework questions. So 474 is our first question, 474-10. So before I do any section, I'd encourage you again, as I did yesterday, just take a skim through what the section was about, because they're going to use those ideas. So what this section is about is inscribed angles, intercepted arcs, inscribed angles being half. If we're inscribed in a semicircle, it's a right angle. And if we're inscribed in the same arc, things get congruent. So what is the drawing of 10 a drawing of? Semicircle. So what did I just read about a semicircle?
What do you?
Right angle.
Right angle.
It's going to be a right angle. If we're inscribed in a semicircle, we would have a right angle somewhere. So where do we have a right angle?
At the C.
At the C. So that would be why this is on this homework page. So if you wrote the given, you wrote the proof, you drew the columns, and you identified that C is a right angle, in a sense you passed the main test of why it's on the page, because that's the idea they're trying to examine from this section. Question about how we knew C was a right angle. Okay, obviously there's going to be more to it than that. So the other given they gave us is that AC, what is AC called? AC is a
Chord.
chord. So they're saying that that chord is getting bisected.
Perpendicular.
So it's perpendicular. Some other section in this chapter, we learned that if you bisect a chord, we're perpendicular. So we'd have a right angle at R. They also are telling you that BC, which is another chord, BC is getting bisected, which means this angle right here
Is right.
is a right angle. They're asking us to make a judgment about what's going on there. Question about how we knew we had those other right angles. That was from probably a section earlier. So can anybody come up with a reason or a thought on what would have to be going on here?
Right angle.
Yeah, why would it have to be a right angle?
Because the rest of them are.
Did we ever learn a fact like that?
It's like rectangles or something.
Yeah, back in like the rectangle chapter, I think we had something at some point that said that if we have 3 right angles in a quadrilateral, that there has to be a 4th one. I think we had that. So we could go that route. There's other routes you could certainly go. We could use one of our friends' favorite theorems. If these are both perpendicular to the same lines, they're parallel lines. What theorem is that?
That's theorem 9 too.
That's theorem 9 too. There you go, right on cue. That is the right thing. So we could use theorem 9 too to say that we're parallel. And then we definitely had a thing that said if we're perpendicular to one parallel line, we have to be perpendicular to the other. We could reason our way out a lot of ways to know that that is a right angle. But yeah, theorem 9 too could be used correctly and get us going there. Do you understand the gist of that one? There's not a proof test for this chapter, so if your proofs are not like spot on perfect, but you're at least being able to use the ideas, that's probably good enough. Question about 10. Anybody else from any of the recent pages, any questions about how to do anything?
Number 2 on 478.
478. So while I'm flipping pages, I'll just take a quick skim and say out loud what I'm seeing. So the next section of reading is, if chords are congruent, then arcs are congruent. And if arcs are congruent, then chords are congruent. There's a tangent secant theorem. So if we're about to see a picture that looks like this, maybe the tangent secant theorem is a thing that we use. But that's the main gist of what we're after, is probably if chords are congruent, arcs are congruent, or vice versa. By which I mean, if this is a match for this, that is a match for that. That's probably where we're going most of this page. So for 2, they say we have a circle on the right with a center P. So circle, center, P. They say PM equals PK. So this is an example of a chord. I used to draw these dotted sometimes, not always, but sometimes. But this RS chord, we're perpendicular, and that is some sort of distance measured that's the same as a measured distance here to some other chord. So to use different words, they're telling you that these 2 chords are blank
Congruent.
from the center,
Equidistant.
equidistant. So if chords are equidistant from the center, you say that on the quiz each time, you fill in every day, equidistant from the center, equidistant from the center. What are the surrounding words there? If the chords are equidistant from the center, they are congruent. So we know that this has to be congruent to this because they're equidistant from the center. So that's like our first idea we could jump on. Chord RS would be congruent to chord TQ. For a reason, I would just put they're equidistant from the center. It's, I'm sure, a theorem number, but we didn't really memorize the theorem number. This was your question, so are you with why those chords have to be congruent?
Yeah.
Does that make sense? So where we're trying to analyze is arc RS congruent to arc QP? And that answer is yes. Why? Chords are congruent. If chords are congruent, arcs are congruent. So that's probably like a 3-stepper. It's probably a quickie proof there. That makes sense? Yeah.
Can you do number 8 on 478?
Number 8 on 478. So 8, we've got AD congruent to CB. So let me just draw part of a picture just to help us not get too crowded. So they're saying something about arc AD. And there is something that's kind of going like this off of arc AD. What did I just like kind of draw a picture of? If I'm talking about arc AD, what did I just do? What else do I have here? It's true. What if I took this away? You've drawn that more often on you. It's an inscribed angle. So what do we know about the inscribed angle compared to the arc? It's half as much. I could have also gone, they drew some stuff over here. If you just look at this compared to AD, that's another inscribed angle. So again, it would be half as long. And another thing that was in that reading as I passed by, it said somewhere here, if we're inscribed in the, somewhere we had a thing, it said if we're inscribed in the same arc or congruent arcs, the angles would be congruent. This would have to match this because this arc is leading us to that inscribed angle. This arc is leading us to that inscribed angle. Those angles would have to be a match. Does that make sense?
Yeah.
Okay. They had given us a little more than that too. They had also talked to us some about arc CB. Arc CB, and I didn't draw this very well, arc CB is supposed to be a match. But if we follow the arc CB idea, this is the same kind of an inscribed angle if we just focus our eye there. And likewise, this is an inscribed angle. If we focus our eye there, all four of those angles have to be congruent to each other because they're all inscribed in congruent arcs. And we could do that in one big swoop. We could be like, we're inscribed in congruent arcs, swoop, all of those angles are congruent. You with that?
Yeah, what would be a reason for, like, if you wanted to do them?
I would just write for a reason they're inscribed in congruent arcs.
Okay.
Or I could leaf through the book and find it's theorem 14, I don't know what number it would be. I think this chapter is easier to just do by phrases, because none of us want to memorize all these numbers. The other thing we could do off of this is, if the arcs are congruent, what thing do we have with that? If arcs are congruent, then chords are congruent. So we could say that these are congruent. I didn't draw that one yet. But we could say that those are congruent. So chords congruent, we're good on that. When you get two congruent things, that's called isosceles. So they wanted us to prove it's an isosceles trapezoid. We just took care of the isosceles part. To be a trapezoid, what's up with trapezoids?
That's a
One pair of parallel sides. So if we look at this side, I'll turn it into a line. I'll take this side and turn it into a line. And I didn't draw this picture well, so they don't look parallel. So just use your imagination. Act like those are the same. Act like those are parallel. If those are parallel lines, this thing that I'm drawing now is called a transversal. These angles match. Those are alternate interior angles, and if alternate interior angles match, that makes the lines be parallel. So alternate interior angles gets us the parallel, that makes like a trapezoid, and then we're...
Man, that was old. What was
That also, yeah, they brought back a lot of chapter 9.
They're reminiscing.
They are. They got, I guess it's the end of the year, they're getting a little bit, you know, what's the word, reflective,
Reminiscing.
sentimental, sentimental for chapter 9.
Nostalgic.
Nostalgic, those are all good words. Anybody else? Homework pages, anything that has people hung up on homework
Can you
pages?
do 3 on 484?
484, okay, so I'll read what's going on here as I flip. So as I'm flipping through, there's the two tangent theorem. So if you encounter anything that looks like an ice cream cone, that is probably the two tangent theorem. And then I'm seeing some stuff with powers and power theorems. So those are like the ones on the quizzes we've been doing that have X's on them. And then we get up to 3, you said 3?
Yeah.
Okay, so 3, we're going to have to draw our own drawing, and that sometimes presents its own sort of challenge to people's lives. I'm going to guess, even not reading yet, it's probably going to be an ice cream cone drawing, because that was the first thing I read about, and usually the homework will kind of go in order. So if the reading first was doing the two tangent theorem, and then they do the powers later, the homework usually will do the same, they'll kind of stick to that order, but let's see. So 3, they say, yeah, they're talking about two tangent segments. So I'm going to go ice cream cone. They say the sum of the length of the two tangent segments, if we put these together, it will make the same result as the diameter. So let's think about that for a second. If two of these together make a diameter, what's a simpler way they could have explained the relationship than saying two together equal a diameter? Any one of them is like a radius, because a diameter is made up of two radii. So if the two radii make a diameter, and the diameter total equals their total, this is probably not the best drawn picture, so I'll shorten this up a smidge. From the center, I could do a radius. I could go like the same distance-ish to make a tangent. I could go the same distance-ish to make another tangent, so it's sort of a stumpy ice cream cone. But this radius matches this radius, matches this tangent, matches this tangent, like everybody's a match.
It's a baseball field.
Square.
It is, rhombus at least, something like that, yeah. What do we know about radius relationship to tangent from way back? They're perpendicular. So we've got a perpendicular there, we've got a perpendicular there. If I want to make triangles, I can do this. I don't know if that'll be an advantage or a disadvantage, but that's available if I want it. Well, let's see what they ask. They want us to find the measure of the angle determined by the tangent segments. Are you with the draw so far? Okay, anybody need me to rewind where we drew? What they're asking for is this total. They want the angle that got determined at that point outside the circle. So I am going to use the triangles. If these sides match, what has to be the case? These angles have to match. So let's do, can anybody do some math?
I'll try.
Like what, how can we generate some numbers? They're expecting us to
Oh,
generate
okay.
some numbers.
Alright, so, there's no right angle
like
where
what
we
we
did
did
with
You remember when
you said they're perpendicular, right?
This is a right angle.
Okay, well, it's a right angle.
Yeah.
so-
These are the same.
So,
We can get some numbers going.
45.
yeah, 45.
Why 45?
Because they're equal, like the sides are equal.
Okay,
and
the
the
triangle has to make 180. This hogged up
90.
90. These share the other 90. And if sides are the same,
And angles.
angles are the same.
Gosh, I'm so intelligent.
So each of these is 45s. Anybody want,
That's 90.
you with that? Okay, so
Yeah.
then what's the grand total at that corner?
90.
That's a 90.
Gosh. Oh.
It is a baseball field.
It was, I didn't draw it great, but yeah, that was a square. Should have been a square if I drew it
Square.
It's
correctly.
the infield and ice cream.
How?
Wow. I don't really.
Something else, pages, anybody, pages, stuck on pages. Anybody, a quick aside and then I'll get your question. The first like 6 things on 484 all involve the two tangent theorem, and probably 7 and probably 8 and probably 9. Everything 1 to 9 to me looks like it's something to do with the two tangent theorem. They all are gonna kind of look like ice cream cones. Would you-
478, 6.
478, 6. 478. Okay, so this, we're back to chords congruent makes arcs congruent and vice versa, being the main theme of the show. 6, they say we have two tangents intersect each other, that they form an isosceles triangle. Okay, this actually, I'm gonna in a sense cheat, because
Mr.
the knowledge we had at this time is far less than the knowledge we have now. Like when 478 was assigned, we only knew certain things. We know more now, and it's going to be hard for me or you to, I think, refocus our brain on what we did know compared to what we do know. Anybody have a thought on 6 of what the picture is going to look like? Yeah, it's going to look like the two tangent theorem. They expect us to draw two tangents, and they ask us to play connect the dots to make a triangle. Why would that triangle be isosceles?
Does the tangents agree?
The tangents are congruent,
Shut
so
up.
it's an isosceles triangle.
Okay.
At the time we did that proof, we didn't know the two tangent theorem. Like as soon as we flipped the page, that's when they did the two tangent theorem.
Yeah.
But now that we learned the two tangent theorem, it's kind of hard to force our brain to like unknow that. I would just two tangent theorem, it's isosceles, move on.
Yeah, I did that when it like was first due, and I spent way too long on that one.
Yeah, I would think so. And it's hard for me to even rethink back to that point now that we're kind of like beyond it.
It was like a 7-step proof.
That
Right, I got it wrong.
could very well be right.
Might have been more. Who knows?
I was trying though. It's good.
Anything else, pages? I think now that we're out of order, everything is fair play on any section. So if you're in like, you're using a fact from 14.8 to do a 14.4 homework.
We'll go back into page
Yes, so
five.
be it. Anything else, homework pages?
492.10.
492.10. So what 492 was about, this is what 492 was about. And at some points recently, we've had the conversation that this formula is basically the same as the distance formula. The distance formula is basically the same as what's super famous thing, Pythagorean theorem. So whether you're using this or the distance formula or the Pythagorean theorem or mixing and matching, that's what's running the show on 492 is those three things, which are really one thing. I haven't looked at the question yet. That's just background of this page. Anything 492, like that versus distance formula versus Pythagorean theorem, play with one of them or all of them. What was your question?
10.
10. Okay, which part of 10? Because there's a million of them. Doesn't matter? Okay, so if I'll just make up a new question.
I'm really just confused how you get to the center.
Can anybody grab the center from the one I just made
Oh
up?
wait, is it just like 4?
3 and
Positive 3
Like
from this.
-4, negative.
It's negative 4 from that.
Oh, okay. Is that all we're doing?
And then the radius is 5.
Oh,
You okay with that?
okay.
Anybody got you there? Let's say I make that 20.
No,
It's
four.
gonna be
It's like
5
3
root
and a
2.
half
Yeah,
or
5 root
something.
2 root 5. 2 root 5.
2 root 5.
Same.
2 root 5.
Oh.
Does anybody need the
It's-
seminar on
It's the
breaking down
exact
those
same thing in
roots?
my mind.
What if that were a 21?
I'm not gonna do that.
Root 21.
Root 21. That's all you need.
Peyton, you're so intelligent.
Something about that.
That's a big brain move.
Oh, me?
If I go like this,
0, origin.
now we're at the origin.
Okay.
The root 21. There might be some that you might have to start to factor a little bit. We did a little factoring seminar, like 11 to 15, you're gonna have to do some factoring by yourself to get those. Some of 10, you might need to do a little bit of algebra, like if I went like this. That doesn't work anymore. What algebra could I do to make this a little bit?
Foiling.
No. What don't we want there?
Opposites.
Opposites. We want to get rid of the 2's. So to get rid of those 2's, you'd have to divide by 2. So divide by 2, divide by 2, whatever you do to one side, the other. So this is 10. Radius now.
Didn't you divide by 2
Root
twice?
10, or root 5.
Now I divided this whole side by 2.
Oh, okay.
So I divided that whole side by 2. So radius,
Just 10.
root 10.
Oh boy.
If I throw you that, you don't want the thirds, so to get rid of the thirds,
Divide by 3.
multiply by 3. So if I multiply this side by 3 to kill the thirds, this would turn into 30. The radius is now
Root 30.
root 30.
How would it